So at EPFL, I specifically work in the Advanced Computing Hub, which is run by EUROfusion. So we focus on plasma physics codes. And so it's a hub as just general place for all the different codes in Europe to go for HPC help. And we find that a lot of these codes have the same problems. And at the moment, that problem is that they need to run on GPUs. So we try and use the same strategies for all the different codes so that we can do the same thing everywhere and test everything out. So the strategy that we usually use is to port using either OpenACC or sometimes OpenMP offload using generic pragmas. And the advantage of that is that it helps us keep one version of the code, because we just have pragmas to add. And you can test it on lots and lots of different machines. Usually they're all available for either OpenACC or OpenMP. So the code that we actually use looks a bit like this at the bottom. So you can see on the top left, we have OpenMP pragmas, and on the top right, we have OpenACC pragmas. And there are a lot of things in common. So the pragma ACC parallel loop gang is different to OMP target teams, but then private IPRT is the same between both of them. And so we can introduce our own pragmas, which at compile time are chosen to be either OpenMP pragmas or OpenACC pragmas. And that means then we have one set of pragmas that we use in the code, and we don't have to have lots of if loops everywhere. So the reason why we want to use OpenMP or OpenACC, sometimes it depends on the machine. On certain machines, we don't have access to OpenACC, for example, on Intel GPUs. But when on the tests that we have done on a V100 and on an A100, we generally get better results for OpenACC than for OpenMP. So for the NVIDIA compiler, we have kind of similar results, but for GCC, we have a much, much better result with OpenACC than we do with OpenMP. And so we want to keep the possibility of using OpenACC for machines where that will make it go faster, but also keep OpenMP for machines where we don't have access to OpenACC. This is generally possible because over the different coding paradigms, they're still mapped to the same underlying hardware. So usually there's a mapping that can be done between the different concepts. So for example, OpenMP parallel is similar to OpenACC parallel or kernel. OpenMP team is similar to OpenACC gang, thread, worker, etc. And you can do the same thing for HIP and CUDA and all of these kind of things, which helps us to write those pragmas. That's the theory afterwards. It doesn't always map so well, but usually it works for what we've done. So in this talk, I'm going to talk specifically about three codes that we ported. So the first one is ASCOT 5, which is used to study neoclassical transports. It's a plasma problem. It's a Monte Carlo particle following algorithm. So we follow the particles until they either hit a wall or they get thermalized, so they cool down. There are collisions, but it's with a static background, so there's no collisions between particles, which means that it's embarrassingly parallel. We can follow each particle individually just until it finishes. But we don't know how long that's going to take. Some of them will collide with the wall straight away, and some of them won't. So it's easy to parallelize in theory, but then you have a big load balancing problem depending on how long the particles survive for. So originally, the code looked like this first block. So for each particle, as long as the particle is running, we continue. And then it's parallelized either with OpenMP or OpenACC. But this didn't really work very well. It works okay, but it's still quite slow. So the first thing that we did was to reorganize this so it's organized by event instead of by lifetime. So here it's while the particle is still alive, do all this. Here, instead, while there are still particles that are still alive, then we do each of the steps for the particles that are still there. And then we have a kind of sort method to say the first n particles are still there. But they then are spread out within the array that we're running over. So that worked quite well. It means that we have a better load balance. But because the particles are all in different places in the array, there are some big gaps, and that seems to have some really bad effects on the GPU. And so in order to handle that, we have a packing step that we added on the end, which reorganizes the array to pack everything into the beginning. And obviously that has a cost involved, but it seems that generally the cost seems to be worth it, because then everything is contiguous memory, and it works a lot better with contiguous memory. So here are the results that we could see. So the Helvetios and JED are the machines that we have here at EPFL. So it's an Intel Skylake and Ice Lake platform, so this is a CPU. And these are the timings we get with those, or for 100,000 particles or for 1 million particles. And then this is the OpenACC parallelization. So the original version, just with a parallel loop, we weren't actually able to run with 1 million particles. It just didn't work. Sorry. But it does work with 100,000 particles, and it takes about 30 seconds. When we added the event-based routine, so that things are grouped by event, then we were able to run with 1 million particles, but we have a slowdown for 100,000 particles of a factor 2, which is quite a lot. So that's what led us to add the sorting and then the packing. And the sorting and packing leads us to a code that is faster, not as fast as the initial version for 100,000, but about 2 times faster for 1 million particles, and it's now possible. So that's obviously better. And there is a cost involved in that. So out of these 277 seconds spent for 1 million particles, we have 27 seconds of sorting and 71 seconds of packing. So that's a lot. If we can work out how to get that down further, then maybe this would be better even for the 100,000 case. Yeah, let me check if it works. The next code that I'm going to talk to you about is CAS3D. So CAS3D is used to study magnetohydrodynamic properties of a fusion plasma. And so it's got a lot of numerical schemes that we're all used to seeing everywhere, like finite elements, Fourier decomposition, and eigenvalue problems. And so this introduces some problems that we haven't seen in ASCOT 5, namely that we need to parallelize on multiple levels. So for example, here we have a loop over different positions, and then at a certain position, we need to solve a matrix equation. The matrix equation can be quite large, so that needs parallelizing over workers, but then the top loop is parallelized over gangs. And that we can do with the pragmas that we've defined. But this has a certain problem on some machines. So on more recent machines, this doesn't seem to be a problem anymore, but on the machines that we have here on the V100 that we have access to, we have an older version of an NVIDIA compiler, and the allocation of a private array doesn't work properly. So we had to find a workaround for this case. And the workaround that we used is to allocate an array with an extra dimension, and the extra dimension then corresponds to the number of gangs. We could introduce more extra dimensions and have one mod Y and one mod X, but then we would have even more memory allocated, and we don't want all that extra memory. So we keep it to the number of gangs, and that way it's limited to the amount that we actually need. But the problem with that is then we need to be able to access the memory at the number of gangs, and that requires a gang ID. In OpenACC, we don't have access to the gang ID. It's not in the standard. It is available in OpenMP, but not in OpenACC. And so the solution that we found when we're using NVIDIA is to use this code that's on the left here. So there are compiler pragmas that are PGI gang index, the worker index, and vector index, which give us the gang worker and vector ID. And so then this is in C. It then needs to be connected to the Fortran code. And then from the Fortran code, we can call these and then use these tab 1 and tab 2 arrays correctly. So once we've done that, this is the the profiling results for the CAS3D code. So you can see this line is where the memory copies happen. Everything was managed. We managed to port basically everything to GPU. All of this is things on the GPU, and then there's very, very little memory copies. So this was obviously a good candidate for GPUs. And these are the results that we saw, depending on different compilers that we used. So on the V100 with GCC, it's a lot slower. But as soon as we move to NVHPC, again, this is an old compiler version, but it's a lot faster, like 8 times faster. And we also tried with Ecole, which is faster than GCC, but slower than NVHPC, and with a more recent version of NVHPC on more recent architecture, where things are, again, slightly faster. And the last code that I'm going to talk about is called SolEdge 3X. It's used to study edge plasma, so the things that happen at the edge of the tokamak. Again, it uses a lot of routines that you're familiar with. So there's a we know method for the advection. There's some sparse matrix problems in there, and there's some linear solvers. And so the idea is to use either OpenACC or OpenMP for the advection and for the matrix construction, but then we want to use other tools such as PETSI, using CUDA or HIP for the linear solvers. And so we needed to couple those two together so that this all works. And so the way that we go about doing that is that we allocate the array that we need for PETSI with CUDA malloc managed. So then that's allocated in CUDA, which makes it available for PETSI. And then when we run the loop, which creates the matrix, we use this command device pointer to tell OpenACC that it's already available. And that lets us then just fill it up in the same way we usually would with OpenACC. And then we can pass it to the PETSI command here. So these are the results that we had on Marconi 100, which is a machine in Italy that we use for these. So the PETSI routines are ported, the bit in blue. That's obviously you see a big improvement, but the other things are still in progress. So the matrix build, I've got it here, but it's not actually coded. So that's why you don't see a difference in the green areas and in the yellow areas. There are still different things that need adding. So yeah, the conclusions that we have are, for the moment, we're porting all the codes that we work on with almost all of them, using OpenMP offload or OpenACC directives, so that we just have one nice clean code base with one set of pragmas. And we can switch using the compiler flags and use the same commands for all the different code bases. But the problems that we're having is that, yeah, the portability performance is really strongly dependent on the hardware and on the compiler and on the version of the compiler and the subversion of the compiler sometimes. And so we have to go through and work out for each machine that we arrive on what compiler is available, what compiler works, what compiler doesn't work. Amongst the ones that work, which one gives the best results, and on the ones that don't work, which ones could work if we use workarounds, and which ones are just too hard to deal with. For the moment, it seems like OpenACC is more mature than OpenMP offload. We tend to get better results with OpenACC, but OpenMP offload is generally available on slightly more machines. But as overall, if we use the right compiler, we can get good performance for the 3 codes that I talked about here. And I presented on the last slides results from Marconi 100. The new machine at the same place in Cinecca in Italy is a Leonardo, which has A100s instead of V100s, and this is about 3 times faster for the first 2 codes that are presented. SolEdge is not really mature enough to have results yet. But generally, as we're doing this, we see that most of the CPU algorithms do have to be modified to get better performance on GPU. So I gave the example in ASCOT 5 that we had everything that was done for each set of particles. It needed reorganizing so that it was done for each event. Sometimes we just can't avoid that. We need to reorganize the code somewhat to get better performance. So I think that's my time.